October 14, 1943. 25,000 feet above Schweinfurt, Germany. Staff Sergeant Tommy Rodriguez pressed his face against the crystal-clear plexiglass nose of his B-17 flying fortress, searching for the ball-bearing factories that would determine the success or failure of the most dangerous bombing mission of World War II. Through the transparent material that his fellow airmen had mockingly called a plastic fishbowl just months earlier, Rodriguez could see German industrial targets with unprecedented clarity from distances that would have been impossible with traditional aircraft windows. The morning had begun before dawn at RAF Thorpe Abbotts in England, where Rodriguez and his crew had been awakened at 0300 hours for what intelligence officers described as the most critical mission of the strategic bombing campaign. The target was Schweinfurt's Vereinigte Kugellagerfabriken, the massive ball-bearing manufacturing complex that supplied 60% of Germany's ball-bearing production for aircraft engines, tank transmissions, and industrial machinery. Below him, the fate of Allied bombing strategy hung in the balance. If American bombers could destroy Schweinfurt's ball-bearing production, they might cripple German war machinery across Europe within months. But the mission required precision bombing from extreme altitudes, where traditional bombardier positions offered limited visibility through small, distorted windows that made accurate targeting nearly impossible. The target lay 300 miles inside German territory, protected by the heaviest concentration of anti-aircraft artillery in Europe and squadrons of experienced Luftwaffe fighters that had been decimating Allied bombing formations throughout 1943. Intelligence reports indicated that German defenses had been reinforced specifically to protect the irreplaceable ball-bearing facilities. Rodriguez could see the approaching industrial complex through his revolutionary transparent nose section, from distances exceeding 5 miles, identifying specific buildings and smokestacks that traditional bombardier positions would have rendered invisible until the final moments of the bombing run. The clarity was so remarkable that he could distinguish individual factory buildings, railway lines, and worker housing that surrounded the primary target. This is the story of how one engineer's plastic nose innovation transformed strategic bombing and changed the course of World War II. But to understand why Carl Norden's transparent bombardier compartment represented such a breakthrough, you must first understand the deadly limitations of conventional bomber design, and why seeing the target clearly from 5 miles away would mean the difference between mission success and catastrophic failure for the men who flew into the most heavily defended airspace in Nazi Germany. In 1941, when the United States entered World War II, strategic bombing was more theory than proven practice. Military planners believed that precisely targeted attacks on enemy industry could cripple war production without the massive casualties of ground combat that had characterized World War I. The concept promised to break enemy morale and industrial capacity through air power alone, avoiding the horrific trench warfare that had consumed a generation of young men. But translating theory into reality required solving unprecedented technical challenges that had never been attempted in warfare. The fundamental problem was accuracy. Bombing from high altitude protected aircraft from anti-aircraft fire and fighter attacks, but made it nearly impossible to hit specific targets smaller than entire city blocks. Early bombing attempts in Europe had produced dismal results. British Royal Air Force operations over Germany during 1940 and 1941 achieved bombing accuracies measured in miles rather than yards. Bombs intended for aircraft factories often struck residential neighborhoods several miles away from their intended targets, producing civilian casualties without significant military impact. The problem was compounded by weather conditions over northern Europe, where cloud cover frequently obscured targets and high-altitude winds could carry bombs far from their intended impact points. Navigation errors meant that bomber crews sometimes attacked the wrong cities entirely, discovering their mistakes only through post-mission reconnaissance photographs. American military doctrine demanded far greater precision than British area bombing campaigns. The United States Army Air Forces insisted that daylight precision bombing could destroy specific industrial targets while minimizing civilian casualties and maximizing military effectiveness. But achieving such precision required technological capabilities that simply did not exist in 1941. Bombardiers needed to identify industrial facilities from distances exceeding 4 miles while flying at speeds over 200 miles per hour through weather conditions that could change rapidly. They had to compensate for wind drift, altitude variations, and aircraft movement while calculating bomb release points using mechanical computing devices that required perfect timing and coordination. Traditional bombardier positions in early bombers consisted of small windows made from standard aircraft glass that provided limited fields of view and distorted vision at the extreme angles required for precision bombing. These windows were designed primarily for navigation rather than target identification, with optical quality that was adequate for seeing large landmarks but completely inadequate for distinguishing specific buildings or industrial installations. The rectangular windows in conventional bombardier compartments created severe blind spots that prevented bombardiers from maintaining visual contact with targets throughout their bombing runs. They could see targets only during brief moments when aircraft attitude and flight path aligned properly, making it nearly impossible to track moving targets or adjust for last-minute changes in bombing conditions. Optical distortion through conventional aircraft glass became increasingly severe at the extreme viewing angles required for high-altitude bombing. What appeared to be a clear view of the target through small windows often proved to be severely distorted when bombardiers attempted to use their precision bomb sights for accurate targeting. The Boeing B-17 Flying Fortress had been designed as America's primary strategic bomber, capable of carrying substantial bomb loads over long distances while defending itself against fighter attacks with multiple machine gun positions. But its original bombardier compartment severely limited target acquisition capabilities in ways that threatened the entire concept of precision daylight bombing. The nose section of early B-17 aircraft featured small rectangular windows that gave bombardiers only restricted views of the terrain below. The windows were positioned to provide adequate visibility for navigation and general target area identification, but offered insufficient field of view for the precise target discrimination required by American bombing doctrine. This design might have been adequate for area bombing of large targets like cities or industrial complexes, but was completely inadequate for the precision attacks that American doctrine demanded against specific buildings, production lines, or transportation choke points. The limited visibility meant that bombardiers often had to rely on brief glimpses of targets through narrow openings that made accurate targeting extremely difficult under combat conditions. Carl Lucas Norden was the engineer whose innovative thinking would revolutionize bomber design and strategic bombing capabilities. Born April 23, 1880, in Java to Dutch parents, Norden had immigrated to the United States in 1904 and established himself as one of America's leading experts in precision optical instruments and mechanical engineering. Norden's early career had been spent developing precision instruments for naval applications, including rangefinders and fire control systems for battleship guns. His work required understanding the complex relationship between optical clarity, mechanical precision, and accuracy under extreme conditions. These experiences taught him that even the most sophisticated mechanical devices were useless without clear, unobstructed vision of the target. During World War I, Norden had observed the limitations of early bombing attempts and recognized that accuracy depended as much on target visibility as on bomb delivery systems. He spent the 1920s developing increasingly sophisticated bomb sights that could calculate complex ballistic solutions, but remained frustrated by the poor visibility conditions in existing aircraft. Norden's background in optical engineering gave him unique insights into the relationship between vision and accuracy that most aircraft designers overlooked. While other engineers focused on mechanical solutions to bombing accuracy problems, Norden understood that bombardier effectiveness depended not just on sophisticated bomb sights, but on providing clear, unobstructed views of targets from extreme distances and unusual angles. The challenge was creating transparent materials large enough and strong enough to serve as aircraft windows while maintaining optical clarity under extreme conditions that no previous applications had required. Traditional aircraft glass was too heavy, too fragile, and provided insufficient field of view for precision bombing operations. The rectangular windows used in conventional bombardier positions were adequate for navigation, but completely inadequate for target identification and tracking. Norden needed a material that didn't exist in 1941, a transparent substance that was lighter than glass, stronger than conventional plastics, optically superior to existing aircraft windows, and capable of being formed into large, complex shapes that could provide panoramic visibility for bombardiers operating under combat conditions. The solution emerged from an unlikely source: the rapidly developing plastics industry. In the late 1930s, chemical companies had developed polymethyl methacrylate, a transparent plastic material that was lighter than glass and could be molded into complex shapes impossible to achieve with traditional glassmaking techniques. The material was known commercially as lucite in the United States and perspex in Britain. It had been used primarily for decorative applications, advertising displays, and luxury items where optical clarity and moldability were more important than structural strength. No one had considered using plastic materials for military aircraft applications, where lives depended on material performance under extreme conditions. But adapting plastic materials for military aircraft use required solving numerous technical problems that had never been addressed in civilian applications. The plastic had to withstand extreme temperatures ranging from -60 degrees Fahrenheit at high altitude to over 100 degrees on desert airfields. Winter operations in Alaska and summer operations in North Africa created temperature ranges that could cause conventional plastics to become brittle or to deform. The material needed to resist cracking under rapid air pressure changes that occurred during combat maneuvers and emergency descents. It had to maintain optical clarity despite exposure to aviation fuel vapors, hydraulic fluids, and industrial cleaning chemicals used in aircraft maintenance. Military operations created environmental challenges far beyond anything encountered in civilian applications. Most critically, the material had to be strong enough to maintain structural integrity if damaged by enemy fire while still allowing bombardiers to complete their missions. Combat aircraft routinely sustained battle damage that would destroy conventional windows, but bombardiers needed to continue functioning even with partially damaged nose sections. Military aircraft designers were deeply skeptical that any plastic material could meet the demanding requirements of combat operations. Conventional engineering wisdom held that transparent materials were inherently fragile, and that aircraft structures required metal construction to withstand combat stress. The concept of replacing structural aircraft components with plastic materials seemed to violate fundamental principles of aircraft design. Norden partnered with Rome and Haas Company, a Philadelphia-based chemical manufacturer that had been experimenting with advanced plastic formulations for industrial applications. The company had developed expertise in polymer chemistry and manufacturing techniques that were far ahead of their time, working with materials that would not become common in civilian applications for decades. Together, they developed a specialized version of polymethyl methacrylate that could meet military specifications for strength, clarity, and durability under combat conditions. The formulation required precise control of molecular weight, plasticizer content, and curing processes that had never been attempted on the scale required for aircraft production. The breakthrough came in early 1942 when Norden's team successfully created large, curved sections of transparent plastic that could be installed as complete nose assemblies for bomber aircraft. The manufacturing process involved heating and forming plastic sheets in specially designed molds that created complex three-dimensional shapes with optical surfaces accurate to within thousandths of an inch. Each nose section required over 40 hours of careful manufacturing time, with temperature and pressure conditions controlled precisely throughout the molding process. Quality control procedures included optical testing that verified clarity standards exceeded those of high-quality camera lenses. Stress testing ensured that the finished products could withstand forces equivalent to emergency dives and high-speed maneuvers. The new design provided bombardiers with panoramic views of the terrain below, while maintaining structural strength adequate for high-altitude operations. The curved, transparent surfaces eliminated the optical distortions that plagued flat glass windows while providing fields of view that exceeded 180 degrees in some directions. But the first prototype installations were met with skepticism and ridicule from military personnel, who doubted that plastic materials could replace traditional metal and glass construction. Test pilots complained that the transparent noses made their aircraft look like flying fish bowls that would shatter under combat stress and leave crews exposed to enemy fire. Ground crew members expressed concerns about maintaining aircraft with plastic components that seemed fragile compared to familiar metal structures. Maintenance manuals had to be rewritten to include procedures for cleaning and repairing plastic surfaces without causing damage that could compromise optical clarity or structural integrity. Critics argued that the plastic noses were structurally weak, optically inferior to glass, and would fog or crack under operational conditions that included rapid temperature changes, vibration, and exposure to chemical vapors. Some bombardiers refused to fly in aircraft equipped with the experimental nose sections, claiming they felt unsafe in what they perceived as fragile plastic bubbles. Military procurement officers questioned whether plastic components could justify their higher costs compared to conventional window designs. Each transparent nose assembly cost approximately 10 times more than traditional bombardier compartment windows, representing a significant investment in unproven technology during wartime when resources were critically limited. But flight testing proved the critics wrong in dramatic fashion. The plastic nose sections provided dramatically improved visibility while demonstrating structural integrity equal to or better than traditional designs. Test bombardiers reported being able to see details of terrain features from distances that would have been impossible with conventional windows. The optical advantages were immediately apparent during test flights over the American Southwest, where clear atmospheric conditions allowed evaluation of the enhanced visibility capabilities. Bombardiers could identify specific buildings and industrial facilities from altitudes exceeding 20,000 feet, providing target recognition capabilities that exceeded the performance of existing bomb sites. More importantly, the panoramic field of view eliminated the blind spots that had plagued conventional bombardier positions. Traditional windows created areas where bombardiers could not see approaching fighter aircraft or observe the results of their bombing attacks. The transparent nose design provided complete situational awareness that improved both bombing accuracy and crew survivability. The plastic material maintained perfect optical clarity under conditions that would have degraded traditional glass windows. Rapid temperature changes that caused conventional windows to fog or develop condensation had no effect on the plastic surfaces. The absence of optical distortion meant that bombardiers could use their sophisticated Norden bomb sights with maximum effectiveness throughout entire missions. Boeing began installing the transparent nose sections on B-17 aircraft in late 1942. The first combat units to receive the modified bombers were initially skeptical, but quickly recognized the tactical advantages provided by the enhanced visibility. The new nose design coincided with the expansion of American strategic bombing operations over Europe. As bombing missions penetrated deeper into German territory and faced increasingly sophisticated air defenses, the ability to identify and attack specific targets became crucial to mission success. German fighter tactics had evolved to exploit the limited visibility of conventional bomber designs. Fighter pilots positioned themselves in bombardiers' blind spots, where they could approach undetected before launching attacks. The transparent nose sections eliminated many of these blind spots and improved aircraft survivability. By mid-1943, nearly all new B-17 aircraft were equipped with transparent nose assemblies. Bombardier training programs were modified to take advantage of the enhanced visibility capabilities. Bombing accuracy statistics showed significant improvements as bombardiers learned to exploit their improved target acquisition abilities. The October 14, 1943, mission to Schweinfurt represented the ultimate test of American precision bombing capabilities. The target was Germany's ball-bearing production facilities, which supplied critical components for German aircraft, tanks, and industrial machinery. Destroying these factories could severely impact German war production, but Schweinfurt was heavily defended by anti-aircraft artillery and fighter squadrons. American bombers would have to penetrate deep into German airspace without fighter escort and attack small specific targets while under intense enemy fire. Mission success depended entirely on bombing accuracy that was only possible with the transparent nose design. Staff Sergeant Tommy Rodriguez served as bombardier in the lead aircraft of the formation, attacking the main ball-bearing factory. His B-17, Memphis Bell Jr., carried the most experienced crew in the squadron and the responsibility for guiding the entire formation to the target. As the bombers approached Schweinfurt, Rodriguez could see the industrial complex clearly through his transparent nose section from distances exceeding 5 miles. The ball-bearing factories were visible as distinct buildings surrounded by worker housing and transportation infrastructure. Traditional bombardier positions would have provided only fragmentary glimpses of such details. German anti-aircraft fire began as the formation reached the target area. Black bursts of flak exploded around the bombers while fighter aircraft attacked from multiple directions. Rodriguez maintained focus on his target despite the chaos of combat, using his enhanced visibility to track the specific building that contained the most critical machinery. The transparent nose allowed Rodriguez to maintain visual contact with his target throughout the bombing run, despite evasive maneuvers required to avoid anti-aircraft fire. He could see the bomb bay doors of other aircraft in the formation and coordinate the timing of bomb releases to achieve maximum concentration on the target. When Rodriguez released his bombs, he could observe their trajectory and impact with unprecedented clarity. The transparent nose provided unobstructed views of the explosions as they struck the ball-bearing factory, allowing immediate assessment of bombing effectiveness. The mission achieved remarkable accuracy for high-altitude bombing operations. Post-strike reconnaissance revealed that over 60% of the bombs had struck within the target area, compared to typical accuracy rates of 20 to 30% with conventional bombardier positions. German industrial reports captured after the war confirmed that the Schweinfurt attacks had severely damaged ball-bearing production. Several critical production lines were destroyed, forcing German manufacturers to implement emergency measures to maintain aircraft and vehicle production. The success of the Schweinfurt mission validated the transparent nose design and established precision bombing as a viable strategic option. Military planners realized that accurate attacks on specific industrial targets could achieve strategic objectives without the massive bombing campaigns that destroyed entire cities. Production of transparent nose assemblies expanded rapidly to meet military demand. Röhm and Haas Company built dedicated manufacturing facilities to produce the specialized plastic materials required for bomber modification programs. Quality control procedures ensured that each nose section met stringent military specifications. The manufacturing process required precise temperature and pressure control to eliminate optical distortions and air bubbles that could degrade visibility. Each nose section underwent extensive testing to verify structural strength and optical clarity before installation on operational aircraft. Installation procedures were developed to ensure proper integration with existing bomber designs. Ground crews received specialized training in handling and maintaining the transparent materials, which required different care procedures than traditional aircraft windows. The transparent nose design influenced bomber development throughout the war. Later aircraft incorporated lessons learned from the B-17 modifications, featuring larger transparent sections and improved optical materials that further enhanced bombardier capabilities. Allied bombing accuracy improved dramatically as crews gained experience with the enhanced visibility provided by transparent nose sections. Target identification became more reliable, reducing the number of missions required to achieve strategic objectives. German air defenses struggled to adapt to the improved accuracy of Allied bombing attacks. Industrial targets that had previously been difficult to hit precisely now faced concentrated attacks that could destroy specific buildings and production lines. The psychological impact on German industrial workers was significant, as bombing accuracy made specific factories and installations obvious targets. Worker productivity declined in facilities that faced repeated precision attacks, compounding the physical damage caused by the bombing. Post-war analysis revealed that the transparent nose design had contributed significantly to Allied victory through improved bombing effectiveness. Strategic targets that might have required dozens of missions to destroy with conventional bombing could be eliminated with far fewer sorties. The technology developed for military applications found extensive civilian uses after the war. Transparent plastic materials became standard for aircraft windows, automotive applications, and architectural uses where clarity and strength were required. Norden's innovations in optical engineering influenced the development of advanced targeting systems for military and civilian applications. The principles of providing clear, unobstructed views of targets became fundamental to precision weapons design. Modern military aircraft continue to incorporate advanced transparent materials that trace their development back to Norden's wartime innovations. Fighter aircraft, bombers, and reconnaissance planes rely on sophisticated transparent canopies that provide pilots with panoramic visibility. The precision bombing techniques developed during World War II evolved into modern concepts of surgical strikes and targeted attacks that minimize collateral damage while achieving specific military objectives. Contemporary military operations rely on principles established through the transparent nose design. Rodriguez survived the war and became a commercial airline pilot, flying passenger aircraft that incorporated transparent windshields developed from military technology. He often reflected on how the ridiculed plastic fishbowl had saved his life by allowing accurate bombing that shortened the war. The Memphis Belle Jr. was retired after completing 25 combat missions and is now displayed at the National Museum of World War II Aviation. The transparent nose section remains intact, demonstrating the durability of materials that critics had claimed would shatter under combat conditions. Norden received numerous awards for his contributions to Allied victory, including recognition from the Army Air Forces and the Navy Department. His innovations in optical engineering established principles that continue to influence military technology development. The Schweinfurt mission became a landmark in strategic bombing history, demonstrating that precision attacks could achieve strategic objectives previously thought to require massive area bombing campaigns. The transparent nose design made such precision possible for the first time in warfare. German engineering reports captured after the war acknowledged the superiority of American transparent nose designs and documented attempts to develop similar capabilities for Luftwaffe aircraft. These efforts were hampered by material shortages and manufacturing limitations that prevented effective implementation. The ball-bearing factories at Schweinfurt were rebuilt after the war using American technology and materials. The precision of the October 14th attack had demonstrated vulnerabilities in German industrial dispersion that influenced post-war reconstruction planning. Contemporary aircraft design continues to benefit from innovations pioneered in the transparent nose program. Advanced materials science has produced transparent composites that exceed the performance of wartime plastics, while maintaining the fundamental principles of providing clear, unobstructed visibility. Military historians recognize the transparent nose design as one of the critical technological innovations that enabled Allied victory through strategic bombing. The ability to attack specific targets accurately changed the nature of warfare and established precedents for modern precision weapons. Carl Norden died in 1965, having lived to see his transparent nose innovations adapted for civilian aviation and space exploration. The optical clarity that had enabled precision bombing evolved into technologies that allowed astronauts to navigate to the moon with unprecedented accuracy. Staff Sergeant Rodriguez received his clear view of German targets on October 14, 1943, through transparent materials that had been dismissed as inadequate plastic toys just months earlier. The fishbowl nose that everyone had mocked provided the visibility that made precision bombing possible and changed the course of World War II. The ridiculed plastic design proved that innovative materials could outperform traditional solutions when properly engineered for specific applications. Norden's transparent nose transformed strategic bombing from area destruction to precision targeting, establishing principles that continue to influence military technology and aerospace engineering. That's how one engineer's dismissed plastic nose revolutionized strategic bombing through material science that provided bombardiers with unprecedented target visibility, enabling precision attacks that shortened World War II and established the foundation for modern aerospace transparency technology.